This is Jason McIntosh with McIntosh Applied Engineering. In this video, I'm going to show you how our SIMA device can be used to detect leaks around microphones. SIMA stands for Surface Impedance Measurement Apparatus. These pictures show a MEMS microphone soldered to a flex circuit. The circular solder pad around the microphone's port is meant to provide an acoustic seal with the PCB it's mounted on. However, if the solder paste and reflow process doesn't form a complete seal, there will be an acoustic path around the microphone's perimeter. Depending on the application, this can compromise the acoustic design. By measuring the acoustical impedance into the port in the flex circuit, a leak in the microphone seal between the microphone and the flex can be detected. However, since the microphone is so small, it's going to be difficult to connect the SIMA device to the microphone. To achieve this connection, a 3 mm diameter tube was fed through a small aluminum plate, which was then attached to the top of the SIMA device. This picture shows the May 131, which will perform the impedance measurement. The black surface shows where the impedance is measured over. It has a diameter of 12 millimeters. We're going to mount this plate onto the 131. And this picture shows the plate attached to the 131 SIMA device. We're going to attach the microphone to the top of the 3 mm diameter tube. However, before the impedance into the microphone is measured, the impedance into an open and then sealed tube will be measured to provide some reference impedances. These pictures show the conditions of the tube being open on the left and then sealed by a piece of putty on the right. If the microphone is sealed, the microphone's impedance should be very close to the sealed tube impedance. If there's a leak, it'll be somewhat less. To keep this video short, I'm not going to do the measurements in real time. This data shows the impedance for the open tube case. The magnitude is in the upper graph, and the real and imaginary parts are shown below. The dotted line is the imaginary part of the impedance. Note that it's dominated by a j-omega mass term on this linear frequency scale. I'll now add the sealed tube condition. It's shown in the green curves. Note that the magnitude is much greater than the open tube case, and the impedance is dominated by a 1 over j-omega volume term. These two curves will set the minimum and maximum impedance that will be seen by the SIMA device. The impedance into the microphone port should lie somewhere in between. Now we need to measure the impedance into the microphone port. These photographs show how the microphone was attached to the tube. To verify that the impedance is accurate, it was measured 3 times, with the microphone being completely removed from the 3 mm diameter tube each time. If we're careful, the impedance should look the same for each measurement, giving us confidence that there wasn't any leak around the blue putty and that the blue putty didn't accidentally plug the microphone port in the flex circuit. Now I'll add the 3 microphone measurements to the impedance graph. Note that the 3 measurements are almost identical, indicating that the measurements were repeatable and so they're likely to be accurate. To get a better view of the microphone measurements, I'll turn the open and closed tube impedances off. 2 of the impedance measurements are nearly identical, while a third is slightly different. However, they're all pretty close to each other, indicating that we should have a good measurement of the impedance into the microphone port. Note that the low frequency limit of the imaginary part is 0, but the real part is heading towards a finite value. This low frequency limit of the real part can be used to characterize the size of the leak. So we could say that the leak is around 175 dB acoustic ohms. It's also possible to get an idea as to the size of the leak by comparing the measured impedance to an impedance of a small slit. This is the Aries window showing a model of the impedance into a slot that's 0.07 millimeters high. This height has been adjusted so that the low frequency impedance of the slot matches that of the measured impedance into the port. I'll plot the model impedance, which is now shown in blue. So it's likely that the gap between the microphone and the flex circuit is around 0.07 millimeters. Finally, the impedance into a second microphone was measured. I'll plot the two open and puttied limit plots and a single measurement curve from the two microphones. This time, the impedance from the second microphone, mic B, is sealed as its impedance is nearly the same as the puttied tube case. So this video has shown how the SIMA impedance device can be used to identify an acoustic leak in a microphone's porting path. In this example, it's just a leak between a microphone and a flex circuit, but it could have been a path into a more complicated structure that would include a mic boot, such as in a cell phone or tablet. Thank you for your time. I hope you found this example useful. If you have any questions, please feel free to contact us at support@maellc.com.